Let's talk about finding zeros of a polynomial. And remember, zeros are roots, are solutions, are x-intercepts. They're all the same thing. And this fancy way of looking at a polynomial just says that it's in descending order, where a sub n is our leading coefficient. And a naught is our constant term. Remember, the constant term is just the number, no variable next to it. So it says if we have a polynomial in descending order with integer coefficients, and p is a factor of a naught, and q is a factor of a sub n, then all possible rational zeros of f of x are in the form plus or minus p over q. Remember that rational, it can be written as a fraction. So it can be a fraction or a whole number, but any square roots that are irrational that keep going will not be included in this list, and neither will our imaginaries. The conjugate roots theorem, we've actually already used a couple of times when we use the square root property. So for instance, when we had x squared equals negative 25, and we took the square root property of both sides, you had to remember that we were using plus or minus, and that's how we got x equal to plus or minus 5i. The conjugate roots theorem is saying that if you have a complex root, a plus bi, then you automatically will have a minus bi, because the plus and minus go together just like they did with our square root property. Next definition, we have the remainder theorem. Says if the polynomial f of x is divided by x minus c, then the remainder is f of c. We actually used that in our synthetic division from last week. Okay, but we're going to take it a step further with our factor theorem. Let f of x be a polynomial. If f of c is 0, then x minus c is a factor of f of x. And you found that out last week because when we were doing the synthetic division, if we had 0 in the very, very last column, it meant no remainder. Okay. And if x minus c is a factor of f of x, then f of c is equal to 0. And again, we found that with the synthetic division. When we did the synthetic division, if we got 0 in the very last column and the remainder column, that's because it was a factor. All right, let's talk about the possible rational zeros using the rational zeros theorem of this polynomial. And it's a polynomial in descending order. Our constant term, our a naught, is 14. When we're doing the rational zeros theorem, we don't need to include the signs. And I'll explain why when we start writing all of our answers. And then our leading coefficient is 4. So we have a degree 3 polynomial, and we would have 3 x-intercepts or 3 zeros. Here we want to try to find the possible rational zeros. So to find the possible rational zeros using the rational zeros theorem, we first need to look at the factors of 14 and 4. So mind your P's and Q's, mind your pints and quarts. So P is going to be our factors of our constant term, which is 14. And then our Q is going to be our factors of our leading coefficient, which is 4. Everybody does their factors different. And if you watch the videos that are included in the problems, they will do them differently as well. I prefer the rainbow method. That's where you start with 1 and the number, because 1 times the number, or here 1 times 14, always gets you the number itself. And then we start moving up. Next number after 1 is 2. 2 goes into 14, so 2 and 7, and I'm making my way in. Next number after 2 is 3. If I take 14 divided by 3, I get a decimal. So 3 doesn't divide 14. 14 divided by 4, same thing, decimal. So 14 is not divisible by 4. Next number up from 4 is 5. That won't divide 14, and neither will 6. Now you may be asking yourself, where's that whole rainbow thing come in? Because if you connect the factor pairs, it starts to build a rainbow. So we have 4 factors of 14. Now we need our factors of 4. We would have 1 and 4. Next number up from 1 is 2. 2 goes into 4. We only have to write it once. And 3 doesn't go into 4. Next number up from 3 is 4. And we're done because it closes out the rainbow again. And the 2 loops on itself. So our possible rational zeros remember in the form plus or minus P over Q. And this plus minus is why we don't have to be concerned about the negative on the 14. So the way that I like to write mine is I do my plus minus and I do my curly bracket. I'm going to take all my factors of 14 divided by all my factors of 4. So I'm going to start by dividing by 1, my factor of 4. 1 divided by 1 gets me 1. 2 divided by 1 gets me 2. 7 divided by 1 is 7. 14 divided by 1 is 14. I'm done with the 1 because I took all the factors of P, the 14, divided by 1. Now I start with my 2. 1 divided by 2 is 1/2. That's new. I need to include it on the list. 2 divided by 2 is 1, already on the list. 7 divided by 2, that's new. I'm going to include that on the list. If you put this in your calculator and you get 3.5, convert it back to a fraction. 14 divided by 2 is 7, already on the list. Because I took all the values of 14, the factors of 14, divided by 2, I'm done with the 2. Next comes a 4. 1 divided by 4, when you do the division in your calculator and convert it back, you get 1/4. 2 divided by 4 is 1/2, already on the list. 7 divided by 4 is new, so we need to include that. 14 divided by 4, when you divide it in your calculator, convert it back to a fraction, we get 7/2, which means we have finished dividing all of our factors of 14 divided by all of our factors of 4. So I can close out my brackets and I have my answer. Watch closely on your online homework because you may have to split it up. You may have to list 1 and -1, 2 and -2, 7 and negative 7, 14, negative 14, so forth and so on. But for your written work and some certain problems, you can do the plus minus with the brackets, which does give us less work. Now, you may be thinking that this is a really long list, especially when we put in the plus or minus and separate all the numbers out. But think that we just took an infinite number of possible solutions and narrowed it down to these 1, 2, 3, 4, 5, 6, 7, 8, 16 different numbers. So all the different fractions, all the different values, now down to 16 of them. If there's a root that is a whole number or a nice fraction, it's in this list. There will not be nice whole numbers or fractions that are roots of g of x that are not in this list.